Good morning and welcome to the launch of our next Electron mission from Rocket Lab Launch Complex 1 in New Zealand. We are on the pad with a dedicated launch for constellation operator HawkEye 360 to deploy 4 satellites to low Earth orbit in just over 17 minutes' time. The local time right now is 5:10 a.m. with liftoff of our 67th Electron rocket scheduled to take place on the dot at 5:28 a.m. local time or 17:28 UTC. The time conversion for Eastern and Pacific is 1:28 p.m. and 10:28 a.m. So thank you for joining us. My name is Muriel Baker.
And my name's James Rattray. It's great to be with you here on another very crisp early morning in New Zealand. We are ready to get the Hawk out of here with the latest launch from LC1. Now, if you've been following along with Electron's exploits lately, you'll have noticed that today's mission is a little bit of a switcheroo from our launch lineup. We've brought this launch ahead of our previous one that's been rescheduled to allow for additional checkouts. Smooth progress is being made, though, to have it back on the pad and ready to launch in no time. But while that's happening, with the rocket for HawkEye ready to go and our launch team ready to fly, we're good to go with this launch from Pad A at Launch Complex 1. That right there is responsive flexibility for our mission partners in action.
For this morning's launch, Electron is headed to a 520-kilometre circular low Earth orbit with 4 satellites in total. A trio of microsats that will collect and geolocate radio frequency signals from around the world, and a 4th satellite called Kestrel OA, an experimental satellite to test emerging capabilities and future technology enhancements. Now, the 3 microsats together are part of Cluster 12 for HawkEye and will operate in a dawn-to-dusk polar orbit to fill a coverage gap in their existing constellation. Today's launch is also the second in a 3-launch contract on Electron for HawkEye. We first launched for them back in 2023 on our very first launch from Rocket Lab Launch Complex 2 in Virginia, which is where HawkEye 360 is based, actually, making them the perfect partner for our first launch out of there. Here's more about their mission.
In today's battle space, threats lurk unnoticed. HawkEye 360 turns radio frequency signals into mission-ready answers through the first signals intelligence constellation. Revealing patterns of hidden movements worldwide, we provide America and her allies with the data, analytics, and domain awareness to act with greater speed and confidence. This is signals intelligence for the modern fight. This is HawkEye 360.
Nice one. We are super excited to have HawkEye 360's satellites back on Electron over here in New Zealand this time around. We've got another 14 minutes and 45 seconds until liftoff, so while we wait, let's throw it back to 2023 when we launched our first mission for HawkEye 360, which was also our first ever launch from Launch Complex 2 in Wallops Island, Virginia, like Muriel mentioned before. Now, that mission was called Virginia is for Launch Lovers, a nod to the US state that both LC2 and HawkEye 360 call home. So let's take a little bit of a look back.
And liftoff of Electron from Launch Complex 2, leaving US soil for the first time and on its way to space up and over the Atlantic Ocean.
I can't believe it's been 2 years already since we opened LC2, and 30-something missions later, here we are again with HawkEye on the launch pad with Electron.
And speaking of, we are about 13 minutes away to liftoff now, which means we are coming up to our go, no-go poll for today's launch. Now, our operators in mission and range control will be polled by the launch director directly for whether they are go to proceed with the countdown to liftoff or if there are any watch items for the rest of the count.
Now, stations are polled across range and launch safety, weather expectations at liftoff, if there's any probability of launch constraints, And of course, multiple engineers monitoring Electron's systems across avionics, propulsion, software, and more. Let's go ahead and tune into Mission Control now to hear the status of today's launch, led by Launch Director Taylor Moore.
We are proceeding with the go, no-go sequence, beginning with stage.
Stage is go.
Avionics.
Avionics is go.
GNC.
GNC is go.
VCon.
VCon is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM.
MM is go.
And LD SUP.
LD SUP is go.
Copy. The go, no-go sequence is complete. We are T minus 11 minutes, 18 seconds, and counting. We are go for the terminal auto sequence at T minus 10 minutes. From this time, the 3-word procedure is in effect.
There you have it. We are a go for today's Electron launch, and the countdown continues. We are on track for an on-time liftoff at 5:28 a.m. local time, still well before sunrise here in New Zealand. And we've got 2 T0 opportunities today, so if there's a delay for any reason in the remaining minutes to launch, then we've got a second chance to try again later in the launch window. So far, though, no watch items for the rocket, payload, or range clearance, so we are tracking nicely to schedule for an on-time liftoff. So while we are busy launching back-to-back missions with Electron, our team at headquarters in California and across multiple states are also hard at work building spacecraft and space systems products for a range of missions, a whole other part of Rocket Lab's business that isn't just building and launching rockets. And so that includes spacecraft, satellites, star trackers, radios, solar power systems, flight software, and many more of the critical components needed for missions to space.
That's right. Now, our spacecraft have supported some really exciting missions so far, like NASA's capstone mission to the moon and another upcoming mission for NASA called Escapade, this time bound for Mars with 2 of our spacecraft. Here's more about what building spacecraft at scale means to Rocket Lab and what our team is working on right now.
My name is Frank Klein. I'm the Chief Operating Officer at Rocket Lab. It's almost hard to believe how much work goes into building a satellite. A satellite that you see back there has 66 different harnesses, multiple systems, star tracker, solar panels, propulsion system, all these different elements that all have to come together.
My name is Anita Becerra, and I'm the Senior Supervisor of Space Systems Production. I have a highly skilled team that allows us to produce spacecraft at scale. What's great about Rocket Lab is that everything is made in-house. So we have things like our reaction wheels, radios, some harnessing, all of those things are made by Rocket Lab, and it allows them to reach our work cells quicker.
I mean, vertical integration is certainly something that differentiates us from a lot of our competitors. I often refer to us being a company that is getting the raw material rolled into the one side of the door, and on the other side of the door, beautiful rockets and beautiful spacecrafts leave our building.
My name is Kimberly Frazier. I'm a Senior Integration and Test Lead at Rocket Lab. So we've taken a panel approach to building spacecraft, which essentially means that we're broken down the spacecraft into smaller parts and we're building and testing it in pieces. It also allows us to swap panels between spacecraft. So if we have one panel that fails or has an issue, we can just pull in another right away. Allows us to move a lot faster.
What really helps us if you build a lot of the components in-house, that you can really look at your system from a holistic perspective. If we just look at the satellites behind us, we intentionally designed the satellite to an ideal stage, knowing what components are going to be added to the satellite. So we optimize not only the satellite, we optimize the components, so we optimize the entire system. And that also allows us to be much faster on the market because we control everything in-house.
This is where our spacecraft build begins. So we have piece parts that we receive. They go through an incoming inspection and they get assembled to a completed structure frame assembly. We have reaction wheels, PPUs, comms plates, and these are all the different sides of the spacecraft that get assembled in this area, and then they get physically integrated into the actual structural frame assembly. We put the first couple of panels on, and that's where we integrate a lot of the bulkier avionics components, and then we hand it off to engineering where they perform a lot of their tests.
Yeah, so the INT team's job is the last piece in the flow. We're really the last group that gets to touch the satellite and make sure that everything is working before it goes out the door. So we're doing a lot of the little checks along the way and helping build those up with production, and then at the end doing the big system level test showing that the whole system works together. I think the biggest challenge is just moving fast. You're more likely to make mistakes or forget things or miscommunication between teams. And so we've really tried to build in those daily tag-ups, very clear work instructions, and very clear processes for this program to make sure that we all know what's going on. And if you're unsure, you know who to ask.
The pure talent that is here within Rocket Lab is absolutely mind-blowing. We're not just building spacecrafts, we're really redefining the space industry. So by having a very high vertical integrated approach, having the best people in the industry and outside the industry getting together, and also being absolutely dedicated every single day, that really makes the difference. And that allows us to grow faster than others. That allows us to be more competitive. Certainly 100% mission success, that's what we all tell our people internally. What that means is that everybody who is doing something within our company, from a design, from a building perspective, we always have the highest standard of quality that we apply to whatever we do. So we test the individual components, we test subsystems, and we test the entire system to just make sure that we always have 100% mission success.
Very cool. And as you saw, lots of spacecraft and hardware with Rocket Lab logos on them. Even the satellites on today's mission will be deployed from a motorized light band separation system built by Rocket Lab, which is a mechanism designed to safely and reliably detach the satellite from the rocket in space. Now, we are at T-minus 4 minutes, 43 seconds and counting on the clock, which means we are heading into the final moments before liftoff to get the Hawk out of here. Here's how those final few minutes are expected to play out. So first up, at T-minus 2 minutes, you'll hear the call that Electron is on internal power. And this means Electron is now running on its own power supply. More importantly, though, it also signals that Electron's flight computer has taken over the reins for the final pre-launch sequence.
Now, after that, we'll hear a call for AFTS, which stands for Automated Flight Termination System. And this confirms that Electron's onboard safety systems are fully active and its telemetry systems are verified to be transmitting data back to mission control. After that, expect to hear confirmation that Electron's liquid oxygen propellant, or LOX, has been loaded and that it's circulating within the vehicle. And then after that, a call should come that Electron's tanks are pressed for flight, and this means that the propellant tanks are fully pressurized, locked and loaded, and ready to unleash the power of Electron's Rutherford engines.
What follows should be a call that high-flow engine purge is enabled, which will mean that the Rutherford engines are primed and ready to ignite. And then last but not least, our launch director will remind operators of their position in the countdown, usually at around 20 seconds to launch, right before taking us down through the final 10-second countdown to liftoff. So let's bring up the audio channels from Mission Control now so you can hear that experience from Mission Control in real time, and we'll be back with you after liftoff.
To all operators, from now on, there should be no red flags in your critical LCCs. Beacon LD on mission card.
LD Beacon.
Please lock the auto sequence and confirm.
Locked.
And please confirm all flight computer ASGOs are green.
All ASGOs are green.
Copy. We are go for auto sequence start at T-minus 2 minutes, and LD is go for launch.
The vehicle is fully on internal power. AFTS is green and enabled for flight.
LOX load is complete. System is in recirculation. Anti-geysering is disabled.
Stage 1 and 2 tanks are pressed for flight.
High flow engine purge enabled.
T-minus 20 seconds and counting. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff.
Stage 1 propulsion nominal.
And the Hawk is out of here for Electron's 67th launch. What a spectacular liftoff for Electron. And that fiery plume lets us know that we are climbing fast and soon we'll be reaching maximum aerodynamic pressure, also known as Max Q, as Electron punches through the atmosphere. Our launch ops team and mission control will be calling out that critical moment shortly, so let's listen in.
Electron is supersonic, approaching Max Q. Cleared Max Q.
There we go. Confirmation from Mission Control that we have cleared Max Q. Right now, Electron is moving at over 2,000 kilometers an hour and past an altitude of 20 kilometers. And our next launch milestone will be MECO, or main engine cutoff, in just under a minute and a half. What that involves is 3 critical actions across Electron's first and second stage. First, the 9 Rutherford engines on the first stage will shut down as scheduled. Next, the first stage will disengage and separate from the second stage. And then thirdly, the single Rutherford engine on the second stage will ignite to propel the mission on its way to orbit. So let's listen back into Mission Control to hear those 3 crucial calls.
Go in roughly 30 seconds.
15 seconds to staging.
Enter burnout detect mode.
Eco confirmed.
Stage separation confirmed.
Stage 2 ignition confirmed.
And there you have it from Mission Control. We've confirmed a successful main engine cutoff. We love to hear that. Now, next up, we'll be seeing the fairing jettison, where Electron's fairing halves actually split apart and fall away. So keep your eyes peeled on your screen for that one coming up soon.
Jettison confirmed.
And you just heard it there from Mission Control, a lovely fairing jettison. You can see HawkEye 360 is well and truly on its way to orbit, now travelling at 8,500 kilometres an hour, just passing 125 kilometres in altitude. What a ride for these 4 satellites.
HVB discharge holding nominal.
Guidance is looking nominal so far into the mission, which you can track in real time with the trajectory plot that will show up on the right-hand side of your screen soon. Otherwise, the total burn time for this second stage engine is around 6.5 minutes to take us all the way to a nominal transfer orbit. Now, the Stage 2 Rutherford engine is practically identical to the Stage 1 engines on the booster, apart from an expanded nozzle that helps to maximise the thrust from Rutherford and improve its overall performance. And we are now at T plus 4 minutes, 32 seconds into the mission, with expected engine cutoff at around T plus 9 minutes.
Alrighty, next up in Electron's series of manoeuvres is the battery hot swap, a move that's unique to Electron, given that its second stage Rutherford engine is actually powered by batteries. Now, since the engine burn lasts longer than a single battery pack can drive the pumps, the propulsion system will switch over to a fresh battery pack in order to keep the engines running smoothly. This happens super fast and can be pretty easy to miss, so keep your eyes peeled for the silver object on the right-hand side of your screen being ejected from Electron shortly.
Guidance is nominal, 200 seconds remaining.
HVB discharge holding nominal, approaching hot swap in roughly 30 seconds.
Throttling down.
Battery jettison confirmed.
An excellent battery hot swap that we saw there, and we heard from Mission Control as well. So we are now at T plus 6 minutes 40 seconds into the mission, with Electron boosting along at more than 15,000 kilometres an hour.
T plus 7 minutes into this mission, you can have a look on the right-hand side of your screen. Our propellant levels are consistent at 29% remaining for kerosene and liquid oxygen. Our kerosene temperature sitting at a balmy 12 degrees compared to our liquid oxygen temperature of negative 177 degrees Celsius. And it's that cold temperature that causes the ice on the outside of Electron when it's on the pad and gives it its distinct black and white stripes. All right, we're now nearing the end of the second stage's journey with SECO, or second engine cutoff, right around the corner. So soon, that single Rutherford engine powering Electron will shut down and the kick stage will seamlessly separate, carrying HawkEye 360's satellites where they belong on orbit. So let's chuck it back to mission control for that critical call now.
Guidance is in terminal, 25 seconds remaining.
SECO confirmed.
Stage separation confirmed.
And there you have it. Mission Control has confirmed SECO, and the kick stage with its HawkEye payload is now in its initial coast phase around Earth. And it will be another 40 minutes or so before the Curie engine on the kick stage ignites to make its final and precise adjustments to place HawkEye satellites to a 520-kilometre circular orbit.
Today we've got two deployments. The first deploying the three Hawk 12 satellites, and then 45 seconds later deploying the Kestrel satellite. So we'll be back with you shortly after a while the kick stage completes that leg of the journey. So join us back for payload deployment in about 40 minutes or so. We'll see you back here soon. Welcome back to Get the Hawk Outta Here, today's mission for HawkEye 360 and Electron's 67th launch and latest mission from Launch Complex 1. Today's launch lifted off at 5:28 a.m. local time from Pad A just 51 minutes ago, providing some bright lights in action on an early morning here in New Zealand.
And Electron cleared through every launch milestone, including Max Q, MECO and stage separation, battery hot swap, SECO, and separation from the second stage to place the kick stage and its payload into an elliptical transfer orbit of Earth. Now, just a few moments ago, the Curie propulsion system on the kick stage ignited to course correct from an elliptical orbit to a circular one in preparation to deploy HawkEye's Cluster 12 and Kestrel 0A satellites to their new home in space. That burn is now complete, and we are just moments away from payload deployment. So let's tune in to Mission Control and listen into those final few moments of Get the Hawk Outta Here.
Cluster separation confirmed.
And that is deployment of the 3 Hawk 12 satellites joining HawkEye's 360's constellation. Now, the kick stage will use its cold gas reaction control system to do a cool little maneuver of flipping itself backwards in preparation of deployment for Kestrel 0A. So let's stand by for that now.
Payload Kestrel 0A separation confirmed.
There we go, payload deployment confirmed. The Kestrel has flown the nest. A big welcome back to space for HawkEye 360 and all the best for commissioning these new satellites over the days to come. And of course, congratulations to everybody on the Rocket Lab team that made this mission possible.
Of course, it will not be long until we are back with our next Electron launch, a mission called Symphony in the Stars. And that one is set to launch from the next pad over from today's launch, Pad B, at Launch Complex 1 again. And we'll share the launch date and launch window for that mission very soon. So keep an eye out on our social media channels and website for all of the details. Otherwise, thanks for tuning in and watching today's launch with us. Until next time, this is Mission Control signing off.